there are various types of projects we do. Homegrown, those are the things I think of from other faculty and staff, and then community on a fee-for-service basis. And this laser tissue fusion device, which is what you're here to hear about, is one of those homegrown projects that we're doing in the lab. And there are a lot of therapeutic and diagnostic uses of lasers. And and actually, this is video, so I can't admit any weakness, right? These aren't the slides I intended on showing. See, and as it was unfolding, I started up the wrong presentation, but this is still a good one. I was going to show you about electromagnetic radiation, but and I don't think that is here, right? Yeah, I do have a slide coming up. But lasers find a number of uses in medical applications of coagulating, sealing off blood flow, cutting, ablating, fluorescing if we add certain chemicals to tissue that, say, will go to places where metabolism rate is highest, then it will concentrate in those places like tumors. We can then cause those to fluoresce and light up to aid surgeons to identify, say, cancerous tissue. We can use laser light for a Doppler effect to look at the blood flow through vessels. But the question is, can we use lasers for wound closure? And can we stitch tissue together? So if we think about what electromagnetic radiation is, it's a self-propagating combination of an electric wave interacting with a magnetic wave in space. I say self-propagating because it can move through a vacuum. It doesn't need a medium for traveling. And what we call visible light is merely a relatively small range of wavelengths in this continuum of very small wavelengths like gamma rays that have very high energy, up to very long radio waves at 10 to the third centimeter, so getting up to even kilometers in length. And the visible spectrum is right in this area. And light is very interesting. No one really understands what it is. You know, on a macroscopic level, we can think of a pair of pliers and feel like we have an intuitive understanding of how that works with a fulcrum and a pivot. But with light, you know, at certain times, it's convenient to use a particle model and think of light as actually traveling as packets of photons, energy. We do know from measurements that light carries momentum, so when it hits a surface, it actually imparts momentum to that surface, much like you would expect particles to do. Very small amount, but still measurable. But other times, like for interference, it seems to obey a wave type behavior. So there's this duality, and no one really gets a handle on what it is because, first of all, light travels at like nearly the speed of light. So we know that matter acts very squirrely once it accelerates to that kind of speed. Our normal physics don't apply. So it is very interesting. And if you think of, if we were to lift up one of these blinds, we have a solid piece of glass here, but if you look, there's Pikes Peak sitting out there. So what we have is light is bouncing off of Pikes Peak from the sun, radiating in all directions. Some of it is coming to our eyes, and we have receptors on the back of our eyes that actually have pigments that are sensitive to this electric field that makes up the light. So it actually interacts with the polar molecules that make up these pigments in order to get excited, which our body then interprets as light. You know, which that's amazing enough to think of right there. But that light that's coming off of Pikes Peak, is it really going through that plate of glass? Or is it hitting the molecules on one side of the plate of glass and setting up a chain reaction within the glass and then shedding off photons on the other side that happen to replicate the photons that were impinging on the other side, like those little balls on people's desks, where you let one go and one ball off the other side flies off. It could be something like that that's going on, rather than thinking about the photon wiggling through. And for example, in the infrared range right here, for infrared energy, it is transparent for glass, but for plexiglass, it is not transparent. Plexiglass is opaque to infrared radiation. It doesn't go through. It's just like a solid wall. So some things are transparent to some frequencies, and other things are not transparent at other frequencies, and we just see a small band. So it may be that we're surrounded by things we just can't see, but they're actually there. So think about that the next time you're alone in a dark room. You hear something. That was the scary part of the program. So if we look at the broad spectrum of the visible wavelengths, and we typically call energy in these bands lasers. They're called excimer. If they're down here on the red end, no, that's the red end. The violet end, there are dye lasers, argon in the middle, helium, neon, nebidium, yttrium, aluminum, garnet, or ND-YAG, over here on the red end. Getting into infrared, this is the kind of laser that would be used for hair removal. If anybody's ever had laser hair removal done, and it basically just blasts away at the root of the hair. Lasers can be used for tattoo removal. So next time you feel the desire to run out and get a tattoo, remember that really what's happening is they're suspending plastic particles in a slurry with alcohol. It turns out that radiator fluid is a very common fluid to carry the particles in, because it behaves nicely, except it's toxic to people. But that's and then the trick is you have these particles suspended in the intercellular space, and in order to get it out of there, you really have to explode the cells around it, and lasers are a good way to do that, because it can penetrate, absorb into those dyes. We can selectively tune our wavelength and basically just explode the pigment underneath, but it's very painful. Welcome.
Hello.
So some of the attributes of laser light that makes it interesting, I mentioned that it is in some ways, you can consider it a wave phenomenon, and in a laser, we generate the light such that the energy coming out is all in step with each other. And it's this property where we get all the peaks and valleys, so we add up the maximum amount of energy, is what makes a 100-watt laser able to burn a hole through you when a 100-watt light bulb will just hurt a lot. But you get more bang for the buck, if you will, out of your light when it is coherent. Another property is the beam is collimated, which is why you can take a laser pointer and interfere with aircraft at far distances, because all the rays of light, all the photons, are traveling in the same direction. Unlike diffuse light source like a light bulb, where they're going in all directions, so the further you get away, the intensity drops off, like the inverse of the cube. Here we get, in a vacuum, no degradation in the amount of energy, because all the light just goes in the same direction. And then it's monochromatic, meaning if we look at the spread of wavelength for the energy, typically a laser beam will inhabit a very tight band of wavelengths, so it's all additive. And just as an aside, for those of you who are teachers, this is kind of cool. After, on a rainy day, if you look in the gutter, you see those colorful swirling patterns on top of the water. Do you know what I'm talking about?
Yeah.
Usually where there's a little bit of oil.
Yeah.
I don't have a board, so you just have to imagine this. What you're seeing is, when you look at that, light from the sun is coming down and bouncing off the top of that layer, so the top of the thin oil layer that's sitting on top of the water. Light from the same packet of light, so it's coherent, is going through that thin layer, bouncing off of the oil-water interface, reflecting up to your eye. Now those two things are, since the oil layer is so thin, they're right on top of each other, and the beam that reflects off the top will interfere with the one that travels a little extra distance through that oil thickness. And basically what you're doing is you're taking white light that contains lots of different colors, and you're shifting one of those two beams that's on top of the other and extinguishing some color, and your eye is picking up all the other colors out of the white spectrum. And the reason you see different colors swirling is because as the wind is blowing or it's flowing, the thickness is varying a little bit. And actually, if you took a picture, you could know how thick the layer is by what color you happen to see, because you would know which part of the spectrum is being extinguished by destructive interference. If I could have drawn a picture, it'd make more sense. I didn't mean to talk about that, but it is a cool thing because you can tell your students to be on the lookout for that after a rain, and it has a nice physical explanation why you can see those colors.